Okay, so let's get started. So welcome everyone to our Thursday Swarm seminar. Today we're really pleased to have our good friend George Vanecek join us. He's from FutureWei. I'll give you a brief rundown here on George. George Vanecek Jr., PhD, is a senior principal researcher architect at FutureWei Technologies Center of Innovation. His group is currently researching Internet of Things emerging solutions for real-world perception, real-world situation modeling, context awareness, and trust determination. George has extensive experience in designing and building software solutions, cloud applications, and service platforms, and has played key roles as a lead developer and chief architect in his ventures. Prior to FutureWei, he was a solutions architect at Cordis, a chief scientist at AT&T Internet Platforms Organization, and a research scientist at IBM and NIST. He founded several software startups after leaving academia as an assistant professor of computer science at Purdue University. He received his doctorate degree at the University of Maryland in 1989 in the areas of artificial intelligence and geometric modeling, where he designed and implemented a non-manifold solid modeling engine to perform near real-time contact analysis and collision detection to support the reasoning about physical objects for a process planning system and subsequently a rigid body physical-based simulation system. That's a mouthful. Go, George. So, with that, I would like to welcome George Vanecek.
Well, it's a pleasure to be here finally, because I've been putting it off. And, wow, I have to get used to this microphone. Okay. So, as you've heard, I do work for FutureWei, actually FutureWei, which is a fully owned subsidiary, the US subsidiary of FutureWei. For those of you who don't know FutureWei, I'm not going to spend much time on it, but they've been making quite a bit of news lately. It's about 150,000 people now, and it is the #1 telecommunication vendor, equipment vendor in the world. We surpassed Ericsson and a couple others, and we're probably the only company that has a complete solution for all mobile services, from cell towers and fiber all the way up to the cell phones and all the radios and everything in between. So it's a very large company, and it's making a lot of news because it is probably the first Chinese company, privately owned company, that is on par, not only on par, but has surpassed some of the biggest European and American companies. And so it's got a lot of people kind of worried about what are these Chinese doing. But anyway, so I'm at the Innovation Center down here in Santa Clara, and I play dual roles. One of them is the strategy and planning, and the other one is exploration research. And exploration research, as part of Innovation Center, is really designed for us to take some of these ideas, these long-term strategies that we're proposing to headquarters and talking to industry leaders around about, and try to build systems that are very kind of disruptive technology systems that would have a huge impact on the industry and stand up not only just sort of the solution, but actually build some proof of concepts, build the initial systems. And then, unlike most groups like us, instead of taking it to some business units to have it built, we then go into the headquarters and try to convince the powers to be that maybe they should be looking at this. Okay, so that's kind of my role. So I had a lot of discussion as to what kind of presentation to give you guys, and so I decided to play it safe and stay away from the detail. But at the same time, because we're trying to have a relationship, I'd like to explain to you where we're heading and why I think what you guys are doing is really great and important, and why what we're doing really has a lot of synergy. And do that as quickly as possible, and then spend maybe 20 minutes giving you an actual demo. So I have a system here that I'm been working on. And it's a very early phase of development, but I think it'll enable me to describe some of the key features and capabilities, and from that we can sort of get a better understanding. And then maybe later on I can come back and talk more about the algorithms and data structures and all the things that are still very much work in progress. So ask questions. How does this work? All right. So I'm running this in LibreOffice. I did it on PowerPoint, so there's going to be some differences. I hope it's not too bad. All right. So I apologize if I'm preaching to the choir, but it's occasionally good to hear a reaffirmation of especially things that we're trying to predict. As we know, no one can predict the future, but everybody tries, right? So the only way to predict the future is to invent it, and the best you can do is to take your best guess as where things are going and then try to push in that direction. So saying that, if you think about what we've done in the 20th century, and I worked for AT&T. I was in Purdue when when we got the first mainframe computers, and there was no network, and we were stitching cables for the first time together. And so I've seen the thing go literally from the early 70s to today, and now looking into the future, we have some major issues here. So these are just some of the relevant challenges that you'll come across when you think about what's happening with the internet and the web, with the growing intelligence and the growing Internet of Things changing fundamentally what this interconnected world is going to look like. There's a huge amount of effort about creating sort of this ubiquitous personalization, individualization within a system. Right now, if I think about it, we have some major issues around the fact that it's still very much a Wild West. I have many different memberships in many different silos of services, and for the most part, they don't really interoperate. And so I don't have a single identity. I don't really have a single presence in a network. I have to go and hope that somebody who owns my data allows me to use it for a while, and then when I die, I can't even remember or know where it is or how to get rid of it or anything of that sort. So how we move towards sort of this ubiquitous personalization individualization is a huge problem that's going to have to be solved. And of course, that's the portal between the silos. I'm not going to go through all these points. I think if you want to, we can drill down at any one of them. Okay. I have a slight technical difficulty here. Did you click on the PDF or the PowerPoint? Okay, that's fine, that's fine. It just all of a sudden appeared, and I had a bunch of icons, a bunch of the resources on the screen, so I think you got the wrong one, but it's okay, it's close enough. So thinking about some of these problems that were listed on that first page, the issue that we're really struggling with is the Internet of Things, the stuff that you guys are very much involved in. And again, I don't have to go through this because I'm preaching to the choir. We're going to have billions of people do real-time communication. I'm also doing a lot of consulting, and I'm working on a very interesting project for, let's just say it's a large television vendor. And the nature of television is changing. So what's happening is that broadcast television is going away, and smart televisions are coming online. And all of a sudden, we may find ourselves that iPads are going to kind of become irrelevant, because would you rather sit with your friend in front of an iPad, or would you rather sit in your living room with a full-screen projection TV, high definition? And I'm not talking 1080p here. I'm talking 4X and even beyond that. I mean, truly immersive, high-definition, personalized system that is connected to the internet and that's streaming data for your personal viewing channel pleasure, right? Think about what we have in place right now to make that happen, and then you realize that things are still changing greatly, and we just have to be ready. When those things when the right things appear for the market to adopt it, so that the money's there to make these things real, that we sort of have the solutions to it. So ultimately, sorry, I'm trying to get my my groove here, because I took this out of a slightly different presentation for a different audience. So I'm trying not to talk down to you guys, but it's very clear that the internet as we know it, or as we've known it, is not the internet of the future, right? And the Internet of Things is going to be driving it. So where it's all heading, and why am I having problems with this? All right, click. Huge delay. And this looks horrible. This looks much better in PowerPoint. I apologize. But it was supposed to be animated. And so what we're looking at here is moving towards what we call the smart connected world. Okay? And we can have a lot of discussions around what this really means. There's a lot of hidden requirements here around changing the nature of how we perceive data services and what we expect systems to do. So to get to the smart connected world is really the challenges. And I'm going to tackle one particular challenge. And the challenge is that we strongly believe that we need to create intelligent systems that provide more intelligence at the edge of the network, process a lot of the data at the edge, and use that to provide additional capabilities for these devices to provide sort of this overall smart connected world. All right, I'm going to accelerate, since those slides were kind of meant for a much more general audience. I'm going to have to switch this. This is not the right present.
You're good. Do it right.
All right. Well. Let's see, where are we? Here we go. All right. I believe that's where I was. Stop. All right, where is it? I should have taken those first 10 minutes waiting for you guys to actually get my act together, right? Sorry about this. Good. Okay, something works. I had to switch screens. All right. Let's state the obvious, because I don't think everybody really relates to this. So back in the 70s, when I started school, and a lot of us old-timers were working, we were all very comfortable having many different people, all of us at the university, punch cards on a CDC 6500 mainframe. So we believed that the world is going to move, and there were some people at that point, well-known people, who claimed, who predicted that that's going to be the future of computing. That we're going to have these big, massive computers, and everybody's going to be connected to them. You know, little X terminals, X11, and so forth. Then all of a sudden, Bill Gates comes along and gives us the IBM PC, and all of a sudden we have one PC per one person. And lo and behold, we come to today where all of a sudden we cannot have enough personal devices. The prediction, however, is that if you look beyond that, you realize that we're actually going back, in some sense, to the very beginning, in a sense that we're going to have lots of devices, but those devices are going to disappear. We're going to become, their device is going to be part of the intelligent systems that are doing things for us on our behalf, talking to each other on our behalf. And so we're going to basically start to share all of these devices. So they're not going to be my devices embedded in a wall. It's going to be my device, maybe that I bought, that's in a wall, but that's now serving you because you happen to be in its proximity. And so we're getting to a point where we're going to have many different hidden computers for many people. And that is going to get us to, sort of, to this smart connected world. So the challenges for the industry here, the way we're looking at it and what we're trying to address is how do we create the infrastructure and the middleware to enable these heterogeneous devices and systems, and that also includes the cloud services and anything in between, and it includes the infrastructure, right, the network itself, to interoperate with minimal human intervention. And what I mean by that is I don't want to configure it or boot it or install it or debug it or all of those things that we need to do. Those devices should just work for us. And in fact, cars are a perfect example. I think they're much further ahead with the car computing technology than anyone else. You walk into a car now, you buy a Mercedes S600 if you can afford it, and you turn the auto drive thing on and you take your foot off and you get stuck in traffic and the car moves slowly and keeps the same distance in the car in front of it. And you're talking on a phone and the car just drives itself. I didn't have to configure it. I didn't have to set the thresholds and velocities and minimums and maximums. That's what I'm talking about. To perform these assigned tasks and to be able to sense, perceive, and react appropriately, based on many of these self-X capabilities. So these self-X capabilities is what we call organic computing. The notion of organic computing is that, as you'll see, that these devices have a lot more ability to sense the environment, understand what they're doing, can modify themselves, and then respond to the environment and to the need, to the tasks at hand, to basically disappear and just do the right thing. So in terms of the organic computing or the self-X capabilities, the next-gen systems must have the intelligence, and by this I don't mean artificial intelligence. I mean something that talks to the points that I just described, to be able to dynamically adapt to their environment, right, to perform these self-capabilities. And not all of them are important, not all of them are going to happen at once, but when I talk about this, and I talk about it to FutureWei headquarters, they're like, yeah, but we're building core switches, and we're building data centers, and we're building cooling equipment and microwave towers. I'm like, yeah. Right? And if I talk to the terminal guys, and they're building personal devices, they're like, and I say, yeah. So in the case of the routers and switches, if you have to set up, if you've ever built a data center, and you pick all the hardware, and then you have to figure out how to rack it and put all this equipment together, what you're really looking for is a router. You just slide a router in a rack, and you walk away. Right? The router figures out how to power itself up. It understands something about the services that are being requested from it. It may negotiate with the other routers, whether it's a load balancer, a failover, or a master or a slave, and whatever things like that. Why do you need to learn Cisco IOS, CLI, and sit there and telnet into it the old-fashioned way, and with some huge amounts of complexity, and writing everything on a piece of paper because you have to remember the settings, configure it to be a load balancer when that feature is missing in that rack, and that's what the service needs, and it's what it's asking for, and the device should simply be aware of that and configure itself, right? So that's the kind of self-configuring capability I'm talking about. Self-describing means that you can have it tell you what the configuration is, in a way that doesn't just dump core or give you some crazy XML of a bunch of configuration stuff. And self-explaining is it needs to explain why it did what it did, right? So it's not just a question of telling me showing me the right configuration file. That's what the current configuration file. It needs to show me that the policies that it applied were based on some reason that I can understand, right? So it has to explain itself, and the rest is pretty self-explanatory. Right. So again, to continue, yeah, this is a repeat slide. So that brings us to the ambient intelligence, right? Now, ambient intelligence is just for these devices to basically understand what it's doing and do it. But it's very much like Hal here, right? Hal walks up to, sorry, what was his name? Dave, thank you. Dave walks up to Hal and says, "Another beer, please." I can't do that. All right, you get the joke. So from existing to, yeah, I can't see it here, so maybe I should stand over there. So from, I don't know why these slides are messed up. I really apologize. So from this, to get to us to be able to do this, we have to first start thinking about the kind of data that these systems can perceive, understand, process. There's a huge amounts of work being done around this, so I'm not going to go into much detail, but we're now understanding that Web 2 is moving to Web 3 and to Web 4 in a sense that we're trying to get machines to understand what the information is, and not just for people consumption. We just don't have HTML files and JSON or XML being pushed into it so that something can render it in the application layer. We're actually trying to write some intelligence or some logic in those systems so that we can use semantic web, and we can use RDF, and you can use other structured forms of information, and we can use ontologies and taxonomies and all that kind of stuff, so that we can write systems that are a little bit more data-driven and data specifically independent, right? And right now, most of the data that's out there is unstructured. That's what machine learning and big data is all about, is trying to find structure in the unstructured data in terms of things like emails and whatever. I would call those semi-structured, right? Unstructured data is very much things like this, sensor data, just garbage. It's just noise until you know what to look for, and then you have to worry about things like calibration, and you have to worry about, deterioration. You have to worry about all kinds of units of measure and various kind of things that might not be implicit unless you have the metadata. So data, and just thinking about data, is an extremely complex problem, and we still, as computer scientists, haven't figured this one out. Okay? And now we're swimming in zettabytes of data generated every year, and it's only this year. Just to give you an idea what that is, if you take that amount of information and put it on CDs, right? How many CDs would that be? Don't do the math. If you lay them end to end, it would be enough CDs to go from here to the moon and back. That's the amount of information we generate in 1 year. That flows. And as I said, it's getting even worse, because going back to the TV, smart TVs that I was referring to, all of a sudden, in the next 5 years, we're all going to throw away our old TVs. We're going to move to smart TVs. We're going to start streaming high-definition H.264 encoded streams from the internet, generated and personalized for your viewing pleasure. And that's going to make this look like the local library. Right? And think about all the data that's related to it. So it all boils down to, we need to increase the intelligence in the system. We need to start thinking about how to build systems that, if you think about it, it's almost like what you really want is you want the hardware, the hardware and network and storage layer. You want the operating system, you want some middleware, and then you want a kind of an intelligent agent layer, and then you want your applications. Right? So you want something underneath there that applications can use to provide this ambient and organic intelligent support without you having to write against it, right? Without you having to implement it. And it's part of every system, and it brings all of these systems together and makes it easier. But ultimately, if you look at these individually, let's not boil the ocean, because we don't know how to do it yet. We know how to do little things successfully or well. So it's really coming down to where they have to perform these 5 things, or at least exhibit some of these. They have to be able to sense. And sensing is just the ability to take some information that comes from, and it doesn't have to be just from the local sensors. It can be information coming from clouds, because for me to know that for me to recognize that somebody walked into a room is great, but for me to understand why that person's in the room, I have to look at their calendar or some such, right? So it's not just from sensor data. So sensing is mostly real-world environment sensing, but it also implies some structured and semi-structured data coming from other places. And it has to perceive it. So sensing simply means that that you hear, but you don't understand. To really understand, you have to perceive it. And that means we look at patterns and behaviors, and you have some understanding of history, and you have some notion of being able to predict or extrapolate into the future. And as a result, you have to be able to adapt. So there has to be feedback loops on the systems, and the systems have to be able to say, all right, I've done this enough times, it's not getting me anywhere, let's prune it, and it's a dead node, remove it. Oh, and by the way, this guy's overloaded, so maybe I should split it, whatever that means, and I'll talk to that. And that leads to learning, which reinforces your knowledge, and then finally that leads to autonomous actions or pro-action or whatever you want to say, right? So high level. Yeah, I apologize if I'm being very vague. But you've seen this, again, right, in different forms. Everybody has this slide. We get lots of data, zettabytes of data, total nonsense. Most of it, 99% is noise, or is garbage. I haven't even said anything about trust, but part of these intelligent systems, you also have to take trust into account. And I have a whole presentation and work relating to changing our notion of the web of trust into a more granular, real-time, evidence-based trust determination where, I mean, we're computer scientists. Think about how we do most of our work right now when we talk to each other. We have a client and a server. Peer-to-peer is almost the same. We have a client and a server. The client somehow is pre-registered with the server, so there is a certificate or some kind of a notion of a membership. He connects to the server. The server says, "Okay, you're one of my members," and he does what you ask to do, right? Trust changes. The level of service changes based on various things. Sometimes that service should be rendered. Sometimes that service shouldn't be rendered. So now there are all these complicated policies. Okay, let's take that out of the systems. Instead, what should happen is that I should be constantly reinforcing my notion of trust and understand when the trust is specific to the context that I'm interested in, bring into play context and intent and situations, so that at any given point when I perform that request, I first ask some trust agent, a broker, do I trust that server with my intent at this situation to identify a particular context? And then the guy says yes. Then I go and connect to him, and the server does the same thing. He says, hey, I know that you belong to me, but do I trust you now with your context or whatever? And it should go and say, do I trust him? And he does his own validation and says yes or no, and then he then performs a service. And that's just the initial handshaking. And as you have a keep alive connection and you keep going back to him for additional services, you constantly reinforce that trust and you constantly reevaluate those requests and those replies. So right now we have no notion of trust as part of our networking infrastructure. Trust is blind. We need to go to real-time, dynamic trust that everybody has. And the intelligent system must have this notion of trust. Otherwise, you will not be able to do anything meaningful. Kind of reminds me of, in the early days, you mentioned my work at Maryland. I was working at NIST, and that was at the time that the auto industry was suffering, and so NIST was trying to help the auto industry to become more agile and flexible cells and all that wonderful things. And process planning and AI was going to solve the problems, right? So we had these AI systems. You did everything on a CAD, and you modeled everything, and then you could refabricate the floor based on this automated process. And so we did a lot of Lisp work and a lot of AI work, a lot of process planning, and a lot of sequencing and fixturing and collision detection, all that stuff. And then we had this big demo at NIST, and we had the whole floor facility. Everything was wired up. Computers were humming along, and we pushed the button, and the thing finally it finally created, milled this piece of aluminum part. And it was beautiful, to a theoretician, academic, computer scientist. That was a feat of astonishing achievement. And then we were doing this to a congressional group and a bunch of senior industry machinists and experts. And one guy walks up and he looks and he goes, "Is that it?" And we're all kind of surprised. "Yeah, that's it." He goes, "Well, that's great." And then he goes back and opens his briefcase and pulls out the same size part that was extremely complex. Hundreds of holes and things that we couldn't even recognize. He said, "You know what this is? This is a Bendix part from a landing gear of an F-16. Can you make that for me?" And we like, "Maybe 20 years. And he says, "Okay, then please leave and don't bother us." Right? All right, but I'm getting off track. The point is that we need to build this. We need to have systems that can take it from data to whatever, and then get data from sensors, and then ultimately the reaction is that you have some actuators that it can actuate. All right. Now I know this is a big order, so let's see if we can do even just a small part. And by small part, I'm not starting from scratch. I'm really looking at what people have done and saying, let's not use some of the techniques that are like really cutting edge. Let's not try some of the current trends where everybody's like, you know, hot to follow these trends because who knows which way they're going to go. Let's try to take some more classic approaches, combine it in a heuristic kind of a, not heuristic, in a hybrid form. Let's combine some classical methods with modern methods around probabilistic and heuristic and kind of neural network form, and let's see if we can create a system, a knowledge base that could perform some of these things. All right, I'll skip this slide. So there's a lot of interest around big data. Much of it is well rooted and has a huge amounts of merit, but there's also a lot of hype in there. Most people don't understand big data. Everything that I set up to now has nothing to do with big data. I just want to make that clear. Why? Because big data doesn't deal with the huge amounts of data that's coming from sensors in a local environment. That is not big data. Okay? Big data is when Google has their services and they're collecting large amounts of data and they're trying to analyze that data and predict certain things or recognize certain patterns from social engineering or from historical information, right? To then train some classifiers to be able to then do a better job of presenting something because they kind of know what the group mentality is. Big data can be used to train something and then be embedded as a training configuration for some classifier inside an intelligent system, but big data itself doesn't really play into that role. Okay. Because it's part of a different presentation, I have to kind of talk to this a little bit. So the AI slide and the big data slide it's saying what I just said. However, it is because of the big data and the machine learning advances that have, in some sense, resurrected AI. Because once again, if you remember that wave, you know, we've had hopes, and then, you know, expert systems are going. Everybody's going to have these beautiful expert systems, and then medical expert systems, and then nothing. Okay, and then, you know, so we've done that number of times now, and now we're finally at a point again where all of a sudden AI is starting to make sense. And why is that? Because we're no longer purist. We no longer recognize. We no longer are driven by the sort of theoretical fervor to prove a point in a specific vertical. We're comfortable recognizing that these things work when you combine them in a sort of interdisciplinary fashion. So when we take classical AI methods, like knowledge bases, right, like decision trees, you know, things that we've done a long time ago, logic programming, you know, predicate logic, you know, first-order logic, you know, all those things, they're improvers. By themselves, they solve very small problems. But when you combine them with heuristic methods, with supervised and unsupervised machine learning to train them, with you know, some advances in probabilistic views, all of a sudden you realize that these hybrid systems, which we would maybe not call AI systems, all of a sudden are solving problems that we could never solve before. And not only are they solving problems, but they're solving problems that people are willing to pay for. And that's why Google is investing billions in these kind of things, right? Because they're making results. So a lot of these things are coming together. So I've talked to this a little bit. So saying that, I'm going to stop right here and present our work. So we're working on eCeNS. eCeNS is a kind of an internal code name. It's a little presumptuous. I apologize. It stands for, E stands for whatever you want it to be. Everywhere, electronic. You ascribe whatever E you want to it. Central nervous system. Okay? And it's because when we thought about ultimately what these intelligent systems are, we're not using the human body or the human brain to model anything, and yet there are some very close similarities that you cannot ignore, like the central nervous system and the central cortex and other things, where different things are being done in different places. And you can sort of start to see how some of these things could come together. So at one end, so what we want is we want a single box. We want a single box that doesn't have multiple engines. You know, you don't want a database and a knowledge base and a theorem prover and a policy engine and whatever, right? Imagine that you could build a single system around a single software design that would have the characteristics of being able to in-source a bunch of sensor feeds, do some processing as we discussed, and then, if need be, provide some actuation on the other side. Or at best, provide interfaces, RESTful APIs, where I can go and query. So what do I want for a perception system? If I orchestrate this room with sensors and I set up some perception or whatever that means, and I want it to do something, whatever that means, then I should go to it. And in terms of the sort of self-X capabilities, I should have the API be able to express to me questions like, what is it that you know? Why is it that you know it? Why did you come to this conclusion? You know, things of that sort, right? So there are 4 major parts in this system. There are, first of all, the domain-specific ontologies. And we all know about ontologies. They're basically graph representations of entities and relations and metadata and constraints that somehow or another, if you don't know about ontology, think about Java class hierarchies, and it's sort of kind of like that. Okay? But the problem with ontologies is that no one can explain to you why what's in them is what's in them. And if you can't explain it, then the system doesn't understand it either, and you cannot program against that. So if I ask you, what is a person? And you say, well, there is that node entity that represents a person in ontology. Great. What are the fields? Well, there's a name in there. There's a age, whatever. And I say, you got 20 properties. Why are they in there? I don't know, just because. Somebody needed them. All right. That's a mistake. That's not data-driven, and it cannot be processed by a computer. And moreover, if you go down that path, you're going to end up doing what the network industry has done with SIM and WebM, the Common Information Model, which is an object-oriented replacement for SNMP and the whole MIB hierarchy. So if you try to model, if you try to build a device, you have to build an SNMP agent, and you have to write your MIB, and then you have to implement that MIB so that SNMP protocol, an agent can connect to it, and using your published OIDs can query the fields of that device. Well, that was very 70s or 60s. So we replaced it with SIM, and SIM is this object-oriented thing. And if you look at it, it's this big, the IETF standard. It's hundreds and hundreds and hundreds of classes. And so before you do anything, you have to basically import this entire monstrosity, and you're going to use only a fraction of it, and you still can't explain why things are in there. All right? So that's what taxonomies are for. Taxonomy is what we use to teach the system how to recognize things. Because if you... I'm not watching the time. How much time do I have?
20 minutes.
Perfect. I better accelerate. So, okay. Think of a taxonomy as a hierarchy, as a tree, where at the root of the tree you have the universe, and at the bottom you have a singularity. So you go from general to specific, from everything to nothing. And what it means is at the top you have a set, and you can't differentiate the members. You just have a set, a cardinality. It's not an ordinality. It's not a. There's no differentiate. There's no recognition. There's nothing that differentiates the factors. So I give you the set, and that set is the data that's coming over some sensor, and now you're telling the system to figure out what that means. So the first thing that you do is you recognize that there are certain sets that have a certain meaning, and that can be described by some external data, a sensor value, usually associated with some unit of measure, Celsius, Fahrenheit, whatever. And you have to partition it for me. You have to say that set has a bunch of subsets. So that category can be broken up to subcategories. And so what you do is you ascribe one or more variables, so it's a multi-parametric space, that says if you give me those variables, based on machine learning or other way of training it, I can then partition it into a set. And now I can differentiate. So if I give you the set of all birds, and I'm finding out that if I put the wrong birds together, they kill each other, then I recognize that there are some carnivores and some herbivores, right? And so if I can figure out some variable that I can figure out from the bird, then I can partition them into one class and another subclass. Now, once I have those two, I may say, yeah, but I like parrots. Well, how could I distinguish a parrot from somebody else? And so you can start to build this hierarchy where at every point you introduce a variable or a set of variables. Those variables come from the external or could be internally computed. But all of a sudden, you're teaching the system how to recognize. But you're doing more than that. Because what you're doing is you're coming up with a global agreement on terminology. So if I tell you I am cold, it is completely meaningless outside the context. Because to an Eskimo, they don't get cold in our environment. To them, it's like they're burning up, right? So cold has a particular interpretation within this categorization, and it's personalized. So my taxonomy, having a common taxonomy is important because we can all agree that warm means something, but then the values, the ranges, or the space that they represent will be different. And so you recognize that so going back to ontologies, the way you start with ontologies, you create a class, and you only associate attributes or properties to that class in that ontology if there is some taxonomy that can differentiate it. Because it's going to be the taxonomy where the data comes in that will filter that data through the taxonomy and therefore assign the values to the class. And so the class will start to understand something about that person, that bird, or the room. Okay? Once you have that, you need to process that. And once you have that, you need to instantiate it. So then you have to make actual instances. And it gets very complicated because these things have constraints, these things are related. They're constantly, everything's changing. It's all very dynamic. And so you need to be able to go in and say, I want a room, but a room doesn't exist without also having the constraints specified, the needed doors and the sensors and lights that are part of it. So you need to, in some sense, instantiate a whole subgraph, or what I say, it's a better description of you kind of have to clone it. And so you clone the ontology, and kind of like DNA, you separate the two things, and then you have this cluster of instances, and this is the beginning of what I call the world model. The world model are those instances, but they are a direct initial image of that ontology and the taxonomy. At this point, I can describe the thing, but nothing ever happens. The system is kind of like a dead-end database. So we need to overlay something on top of it to make it work. So what do we have? We have state transition diagrams, we've got workflows, we've got neural networks, we've got all kinds of different methodologies to do that. So we recognize that what we got to do is we basically have to adopt the sort of the neural inspired kind of a network and overlay the world model with a kind of a neural network, so that that network propagates information throughout this world, throughout the world model. So when I say neural inspired, I'm not talking about neural network neurons, which is the way we model neural network with sigmoid functions, stuff like that. I'm talking about symbolic networks. I'm talking about neurons that can have arbitrary functions, closures. And then the question is, what is the minimum set of necessary neuron functions to create this perception, within the world model? So saying that, I'm going to give you a demo. Okay? Because it gets very complicated, I'm going to do a very simple example. I'm going to build you a perception engine for a room like this that has a furnace that can and an AC, and there's a light and a light sensor. There's a temperature, and obviously it's an environmental variable with a thermostat, and there's a door sensor, so I know whether the door is open. And just to make this simple, because it gets really complicated, or could get complicated, I'm just going to assume that I want to keep the room warm if the lights are on and the doors are closed. So if the door is open, I'm heating the outside. I won't do that. If the light is off, no one's in the room. You get it, right? I mean, obviously, we can make it much more complex. And we're gonna stand up, but it's gonna show some of the basic properties. Okay. So you have to bear with me. All right, where is it? I did not come prepared for this. Sorry. All right. So this is a one-page rich JavaScript client. If you know what that means, that completely written in HTML5 and D3. No jQuery, no other support library. And it is supposed to be sort of the modeler's manual interface into the perception engine knowledge base. Most people will never see this. Instead, there will be other interfaces on top of it that will be more user-friendly, customized, right? But just to kind of give you a sense, this is what it is. So I'm gonna build this from scratch. So we start off, and we're going to call it the furnace, and it's going to be the house temperature demo. And so what we have here is we have the root of the knowledge base of the perception engine. It gives you the world model, the taxonomy, and the ethology. Right now they're separated, but actually even this is too simplistic. I'm not showing you the whole thing, because if you think about it, the system has to understand different domains, different uses, different contexts. So think of this as a subtree of a slightly more complex, higher level. But again, the rest of it is pretty straight. It's almost like a standard entity relational model, right? And you got relations, you got nodes, whatever, right? Who cares? All right, so very quickly, I'm just going to step through this. So I'm going to come in here, and I'm going to create a house and give it some constraints. For simplicity, I'm not showing you all of the details. Otherwise, we would be here much longer. Now, you're asking yourself, okay, but no one's doing this anymore because this is manual and nobody's going to program this, and everybody's trying to figure out how to learn this from first principles. Well, before we run, we got to learn how to walk. So there's always going to be some initial bootstrapping where you're going to have to create a model and then let the system organically expand itself. Without that model, without a frame of reference, there is no, you're not going to build the universe from a singularity. You have to create, you have to at least impose the rules of physics and then turn on the engine, right? So that's what this is for. Let me turn off these things. So we're going to, a house is going to have some door. The screen is too small here, sorry. All right. Now let's see, maybe I can make it a little bit smaller. Right, it's going to have a door. And the house is a furnace. So there's exactly one furnace. And the room has a sensor. It has a multi-sensor. So it has a sunspot sensor. Sunspot sensor. It's just one of many different kinds of sensors. It uses Bluetooth or Zigbee or whatever, and it has a light sensor, temperature sensor, motion sensor, and a proximity or single strength or some such. Okay, so I create a sensor. So now let's look at it. All right, so these are classes. I'm starting to build an ontology here. And you can map this to RDF and export it and do all kinds of things. But it's meaningless. It doesn't do anything. It doesn't represent anything because I didn't tell it how to recognize things. And a house doesn't. So what am I interested in a house? When I go to the system, this system will do something because I'm going to ask it, what can you tell me? It's going to say, well, I can tell you about a house. Well, what can you tell about a house? Nothing. Right. So I have to teach it around some physical properties. So I'm going to switch over to the taxonomy, and I'm going to define something for it to recognize. So I'm going to say, okay, we're going to have a temperature. And that is in Celsius. And, whoops. And I'm going to go from minus 100 to 100. Okay. Now, this is a category. This is a subcategory. The category represents the entire set. The subcategory represents a subset. In this case, I didn't tell it how to recognize anything, so it only has a single subset, which is the set itself. And I'm going to, therefore, teach it. Now, we can do this through machine learning. It can iterate and split and recognize certain categories. Right now, I'm going to sort of help it along to kind of get things started. So I'm going to say everything below 100 is going to be called freezing, and everything above 100 is going to be called cold. All right? And let me freeze this. Sorry. I'm going to split cold because now notice the cold is from 0 to 100. So I'm going to split it at 10. And above 10, I'm going to call it warm. Whoops. This is really hard looking at it sideways. All right. Freeze. All right. And then above warm, I'm going to split it, and above 20. Now, don't get me on the exact numbers. The numbers are really not that important. Right. So now what I've done is I have eliminated the need for complicated expressions that deal with the mathematical equations for rules. Because now, instead of a rule, I brought the first order logic into predicate logic, because now all you have to say is it warm? You don't have to say, is it greater than 0 and less than 10, et cetera, et cetera, et cetera. You can just simply say, is it warm? Because that category has within its hierarchy, within its taxonomy, all of the information that it needs to recognize itself. So if I give me the sufficient set of sensor data, I can now do that. And so what I'm going to do is, now that I have that, now that I have this temperature, I can very nicely go to the sensor and say, hey, I know that you know about temperature, so here you go. There's your temperature property. Now, observe that this property is represented as a node itself. Why? Because properties are complex things. They have metadata. Okay? It's kind of like Shrek. You know, it's complicated. They have onion layers. And one of the properties of these properties is that they have histories. I'm not showing you them, but they're also representing as nodes. So what happens is as information flows into that property, I can say what's its value. But I can also say what was its previous value, and what was the value at a certain time, and what was its maximum, what was its minimum, what was its average, is it increasing, is it decreasing. So all of a sudden I have a history. Now as it turns out, I must also have history for the taxonomies and for the world models, because entities change, relationships change. And so the system is designed to capture full histories around the link structure as well as the properties. So let me go and let me quickly do the other one. So I need light. and that's in lumens. Now, obviously, here we can have more than these. I'm just having some basic units of measure. In a real production system, you would preload that with, whoops, where did it go? There it is. All right. And so I need to define, what light means. So I'm going to say below 200, it's dark, and above 200, it's dim. And then I'm going to split that as well, and say that 600 is good. So above 600, it's bright. So I have a variable adjustable. I can go light. In different densities of light, and I just choose to. I'm sensitive to light, so I'm saying, I don't want it to be bright. I want it to be dim. So again, the system now understands what I mean by bright. And your notion of bright could be different because, as you'll see, the taxonomies are replicated or cloned along with the ontology in order to create the world model, so that while we agree on the term and how it belongs, in a meaning, what is dim? Oh, that's a kind of light. What's its properties? Oh, that's a unit of measure of lumens, right? We don't have to agree on the thresholds. And so then I'll give the sensor. So I'll give the sensor the light property, and then finally I will define. And this one is different. I will define the door status. Now, as it turns out, door status. I'm assuming here that the door status is arrived from a sensor, an intelligent sensor that doesn't just send back motion information. It sends me the actual value. So it's a cardinality. The numbers don't matter. What matters is that they're unique. And so I'm going to say closed and open. Okay? And likewise, I'm going to, okay, now I'm taking liberties here. Obviously, that means that this door sensor would have to be attached to this sensor would have to be attached to the door, and if you close the door, maybe it won't detect the light because the door's in the way. But again, for time. So now what I do is, now these are the actual values that come from the sensor data, but I'm not interested in it. I need the system to know about the subcategories. So what I'm going to do is I'm going to tell it. So the room still doesn't know about this. So I'm going to go to the door, and I'm going to add a kind of door to it. And so notice that this is called door status. It's called kind of door status. And that's just a prefix that I use to define the subcategories. So if I look at the properties of it, the door is the units of measure, the light. Let's do it as an example. The light here, and I'm going to give it to the room. So this property associated with the room is the subcategory of light. It's the kind of light. So in that bucket, you're going to have the values for bright, dim, and it's going to change based on a sensor. And what you're seeing here is an introduction of what I would call these neurons. So we have been working very hard to identify a group of neurons that get automatically created based on some design patterns or perception patterns to automatically build the neural networks to resolve all of the state transitions. Okay? And what's nice about them is that these will be cloned in the world model, and consequently, we will be able to assign analytics with each one of these so that later on we can decide, we can do some probabilistic analysis on a network in terms of how many times these neurons are executed and so forth. And if you think about it, this whole perception engine, the engine is about 20 lines of code. Because all that the engine is doing is saying, it's a non-deterministic engine that, well, it's implemented deterministically, obviously, because, but there's a queue, there's a priority queue, and the way that system will work is that when the value appears here, it excites this neuron, the neuron gets scheduled for execution, and then the engine simply executes the method based on all its inputs and generates some output and assigns it to this guy if it fires. And then the neurons just keep streaming. So the neurons get processing, and the network gets deeper and deeper, and at some point it gets a certain level of sophistication. So to finish this, I'll do a couple more things. So I'm going from categories to subcategories. Here I know about the door status. Here I know about the light. I'm missing one. Door status, temperature, right? I have temperature. Oh, sorry. It was hidden for me. Okay, and I'll give the room a temperature. All right. So now the room knows about the kind of light, the kind of temperature, and kind of door. Okay, I put it in the wrong place. That should have been on a door, but excuse me there. So now what I'm going to do is I need to tell the furnace. So I don't know how to describe the furnace. So I have to first describe the furnace. I have to say, well, the furnace status is either off, it's cooling, or it's heating. Okay, and because I have that, I can now give that to the furnace. And because now furnace knows about its status, the desired status, I'd like to change this based on these properties. So what I do, now the attempt is that the system will be able to do this automatically, but for now we're going to do it manually. So these are the three operands that are necessary for resolving all the possible states to this furnace. Okay. I mixed in the wrong one. I want the subcategory of furnace, right? Because ultimately, these guys don't know about the values. They know about on, off, and cooling. So let me try it again. I choose these guys, and then where's my kind of? This one. All right. So now I'll add this rule. Now at this point, the system says, "Now wait a minute. There's 2, 3. There are 24 possible things that can happen, and you need." So what you're doing now is you're incorporating logic programs. These are horn clauses. And you have and you need to keep a sound system. And so what's happening is between these properties and that properties, there's a logic program. That's a sound and complete program, meaning that you have to resolve all of the states. And then any one of these gets excited, it'll modify that property based on the neurons. And because these are mutually exclusive, in this particular, there's no probability here, there's no fuzzy logic. So exactly one and only one of these is going to execute, right? But if you were to introduce probabilities into it, then you can see that multiple neurons then can change the value simultaneously. And then we get into some interesting things, but let's not go there. So just very quickly, if we said, okay, so we said if the light is off, if it's dark, then turn off the furnace. If the door is open, turn off the furnace. And if it's not dark and door is closed and it's freezing, then heat it. And if it's warm, cool it. All right, you get the point. So it creates now most of the time it will not show these in this way because it can get pretty cluttered. But these represent one or more clauses in the logic program for this particular state. And the system can now think about how it works. This is not theorem proving. You're not proving anything. You're not looking for, you're not doing resolutions. You know exactly which neurons to execute, because there is a very natural flow. The only thing that you have to do at this point, and I kind of messed it up with this guy, so ignore him, is that I need to have an actuator so that if these guys get set from an external sensor, when I set that value, it sends a message to the furnace. And that is no longer the subcategory. That's my interpretation. It has to be the category that has the actual values. And so I'm going to add a furnace property that maps it up to I mean, if you look at these properties, okay, sorry. Anyway, it maps it. These go from categories, they go down, they specialize, and these guys generalize. They go back up, and then this guy can be set up as an actuator, which goes out. So I can continue on it, but let me show you how the system works. So I'm going to stop here because I don't have time, but here's what would happen. First thing that I need to now do is create a room for it. So I would choose the house, and I could say instantiate. And this cloning process would happen. And the reason why I call it cloning is because the instantiation should propagate throughout the entire taxonomy and ontology based on the constraints, right? There are all these different constraints and some metadata, and based on that, it'll create an instance of some notion of this environment. At that point, the system scans the world model. It looks for all of these properties, dynamic properties. It identifies the properties that have no incoming neural connections. And it's asked the question, this will never be executed. It's either a static property, like address, which will never change, or it's a dynamic property, in which case something has to give me that value. So at that point, it automatically registers itself as a potential sensor. And because that dynamic property is associated with the category, which has the units of measure and everything like that, it knows exactly what kind of data it needs. It gets a little bit more complex, but take it for granted. So when messages come in, there is a server that receives external messages, maps them into these external dynamic properties, and assigns them. And so the history, it gets assigned. That triggers the neurons. The neurons propagate, values propagate, and at some point the thing stabilizes, or it hits some actuator property, in which case something happens. So let me show you what that looks like. And then I'm done. So here's another view of that. So here you're looking at the instances of the world model. And so these are the instances. These are the neurons. These are the taxonomies that have been personalized. Because I can adjust. So if it's too hot for me, I still want it to keep warm. I can adjust the value of warm, the thresholds between any of these, right? If I so choose to. But the key here is this. Here is this furnace. Let me move it up here because you'll see why in a second. Now, this is an earlier version, so I don't have all of the nice editing features of the thing, so it doesn't look quite as nice, but you'll get the point. So what I'm going to do is I'm going to turn on the perception engine, which is basically the network, the neural network. And I'm going, since I'm doing this offline, I'm going to turn on a data generator. So since it knows which external properties need to be filled, it just starts to feed some periodic data into it. And you're going to see the states change. So I'm going to turn that on, and what you'll see is not the whole thing. All right, so where is the cursor? Where's the mouse? Come on. You can do it. All right. Well, suffice it to say that guy changes colors, right? All right, so let's just watch something. So if I sit here, I can open and close door, and you can see that up here it was told that the door is open, and I can close it, and now it finds that the door is closed. And I can turn the thing on, there's dim. And someplace in the network, the thing turns bright, right? Because the data comes in, it gets mapped through a taxonomy and it will propagate through the neurons, the logic programs, into other things. So ultimately, maybe I can change this side. Come on. Here we go. Just have to grab the right corner. Fine. So remember, we programmed it. We programmed it so that if the door is closed and the lights are on, it cools it. So in here, I can watch the temperature. Sorry. Where is the, here we go. Right, so what happened is that I turn on the lights and I close the door, and so this guy started to increase heat and the temperature went up, and obviously the network converges to the right things. Let me just kind of play weatherman and crank up the heat outside. So if the heat rises, notice that the furnace is now cooling. All right, I'll stop here. So what we're doing is we're expanding the system to first think in a sort of general terms as to what are the basic requirements of such a system in terms of how do we feed sensor data into it, how do we take actuator data out of it, meaning activate something on the outside, how do we describe what we can recognize, how do we describe what we want to describe, what kind of interfaces we need in order to interrogate this, and then ultimately there's a number of open problems that we're collaborating with you and others to resolve around things like context, trust, and other things. So in terms of context, let me just say that and leave it at that. One of the things that you cannot do is to build a static network. Our brain doesn't work like that. When you get into a car, you instinctively know where the brake is. You don't look for it. You don't have to relearn where the brake is and have an accident looking for it because you already know. And you knew that because the neural pathways got rewired. And that's what context is all about. So if you introduce context into this, then we have neurons that are of the type of modifying other pathways. So if you have two contexts, and those two contexts refer to the same things underneath, you may choose one of these contexts over the other context. And so what that means is that when some data comes in, like you're listening to something and you hear a bell, there's a neural connection connected to this context subgroup. But when you change context, that is rewired and it is flipped to this group, so that there is no searching, there is no complex analysis. It simply knows because you told it that when the bell rings in this context, it's not this response, it's this response. So these connections right here, there are neurons that point to neurons that have incoming, they would have an incoming trigger, they would have an incoming set of informations from multiple contexts, and then when they get triggered, they would take this particular neuron and rewire it, right? And that allows us to make the system extremely efficient so that it doesn't make the same mistakes over and over, or it becomes trained through reinforcement to move to certain nodes or to in this case, certain properties. Okay.
Let's give people a chance for questions real quick.
So.
Thank you, George. I know we're running late, but I wanted to give people a chance to ask questions if you have.
Sorry,
So, what? Use that. Oh, thank you. So I was kind of curious. It took you a little while to build this network up, obviously, because you were doing it manually. So
yes.
You kind of hinted that there would be some automatic building of such networks. Do you have any ideas on how that would work?
No.
Oh, okay.
Well, yes.
Because I've actually built, I've built home automation systems like this before, and they're always very painful. I mean,
that's correct.
Lots of individual connections.
And that's where the machine learning comes into play. So, look, I think the word hybrid is, extremely important. I think what we're saying here is, if you're going to sell somebody an intelligent system, okay, let's define differently. This can be the common infrastructure or common core, which is the thing inside the different intelligent systems. Okay, but each system is built for a particular vertical. So, for instance, this is not being designed to do the full recognition and learning. It cannot do that. it is not being designed for that. What it's being designed for is that can I put some small piece of code inside a system and then train it to perform certain tasks. So the majority of the complexity comes from pre-designed ontologies and taxonomies. But the system has some extensions to, as you saw, you can very easily take a taxonomy and refine it. When you refine a taxonomy, you're teaching it how to recognize, how to be more discretionary, right? Instead of like classifying everybody together, you can now recognize people with hats. And so when you have a category of people and you're differentiating people on the presence or absence of hats, if you just recognize people, you could then say, now I have this variable called hats, and now you can partition people with hats and without hats. And that can be done dynamically, and that can result in some connection being split. So let me see if I can explain it. If you have a taxonomy with 3 things in it, then ultimately there is that value in a category is here. The thing that you're interested in, subcategory, is up here. You have a path, you have a neuron between it, and it basically looks at the values and some equations in here to differentiate between them. Now you introduce another one, but you don't introduce another one. What you're doing is you have one dimension, and what you're doing is you're splitting a dimension. So you're splitting a range. So you're saying, you're not introducing any values. You're still within the minus 100 to 100, but you're saying in this range I'm calling it something else. Well, that is a name that doesn't exist, and this neuron doesn't know about it because it's being said, if you see warm, do something. If you see hot, do something. And now you're introducing hats or whatever, and so you now have the system isn't sound anymore. And sorry, it's not complete anymore, right? But what happens is that when you split that category, it automatically propagates through the network, and it will replicate that category into 2 subcategories. One that was the original one, and one which is the new one. And now what you have is you have basically 2 redundant paths, but you have a path that refers to something that you just recognized. That means you can start tweaking its attributes in terms of probability of success or based on some of the analytics. And so the system can start to learn by you simply refining or teaching it how to recognize better. And we're working through the algorithms that can propagate that through the network. And in that sense, the system can learn. Now, there are other things. This is just one of several. There are other methods like that that we will try to apply to build different kinds of connections. But the problem is the original ontology. We don't know. At this point, I have no idea how to expand on that ontology without you telling me. Sorry, that's a long answer.
Are there quick questions? Nope. Well, thank you, George.
Thank you.